Okay. Good evening, everyone. Again, my name is Shehza Said, and I am a third year research scholar at IIT Roorkee. So, this is our sixth interactive session for the course of Geotechnical Engineering 2. And today we will be doing some numericals based on what you have studied in your week 5. So, last time we did some numericals on to be specific, we did some numericals on consolidation settlement for foundations. Uh, Before that, we did immediate settlement. Last time, we did consolidation settlement. And for week 5, you have covered geotechnical explorations methods, exploration methods, and we will be dwelling in some aspects of this geotechnical explorations. More particularly, we will be talking about the standard penetration test. So, this is the question. The SPT results at various depth in a sandy soil are given in Table 1. A donut automatic trip hammer with an efficiency of 80% and a standard sampler were used in a borehole of 150 mm diameter. The ground level is deep and its effect can be neglected. Determine the corrected N values, estimate the soil friction angle, estimate the variations of relative density with the depth of sand, estimate the average value of modulus of elasticity, and if the water table is at 3 meter depth, determine the corrected N value. So first let us excuse me. So first let us talk about the SPT test for a little bit, and then we can see how we can tackle these problems. So give me a moment, please. Okay, okay. So SPT test basically developed in the United States around 1920s. When we have a particular site, uh, what we want to know usually is this about the soil there. We want to know the stratification of the soil. For example, if I have a soil, so if we have a site, we want to know the stratification. Why? Because, for example, if I have a dense sand with good C5 properties here, and I build a foundation here. So the load on the foundation is carried in the form of a bulb through the soil. So if this bulb is going through multiple strata, we need to be sure that the settlement in all these strata, in whichever strata it is going, is not excessive. For example, if I have a weak layer here, so there will be excessive settlement here leading to excessive settlement of the foundation. So we want to know, especially within the this pressure bulb of this foundation, about these soils. So for these, we do these penetration tests because we want to know about the strata. Now, there is a standard penetration test And then there is also cone penetration test. So what we do in standard penetration test is that we take a sampler, which is usually a split spoon sampler in this case, and we attach this with these drill rods, and then we take this hammer that has a mechanism to be guided along guide rods, and then we release the hammer to a given height, which is in this case equal to, let me confirm the exact values, almost 76 centimeter is the drop of, because these are the standard specifications. Otherwise, we will not be able to compare any two results if we do not standardize these specifications. We drop this hammer, and this hammer also has a standard weight, which is about um, uh, 622 Newton, about 65 kgs or something you can convert. Uh, so we have a particular hammer with a specific weight, with specific fall. So basically, what we are standardizing is the energy that we are inputting here. And then what we calculate is that how many number of blows it takes for a standard penetration. So in SPT case, what we do is we count for every 150 mm. Okay, and then um, for three, uh, we take uh, up to 450 mm, we count, and then we discard the first reading. The purpose of this first reading is for seating, so that there is no contact, there is no error due to improper contact or something like that. Okay, so we take this standard hammer, drop it to a standard height, and then we count how many blows it takes for a standard penetration, and then that is how we standardize this test. And the thing to keep in mind is that in this test, this is not a continuous, it does not give us a continuous profile. In fact, we will take one sample at 150 mm, for example, at top we will take, and then we will go 1.5 meter down. Usually, normally it can be spaced largely or uh, less than 1.5 meter if we encounter, if we know through boring that we are encountering a different layer. It can be varied, but normally it is 1.5 meter. We take another SPT sample here, then we take another SPT sample 1.5 meter below. So we will know the N at here, we will know it here, we will know it here, and between these we will not know the N value. So that is why it is not a continuous as compared to the cone penetration test. The cone penetration test will give you the resistance to the penetration throughout the profile. So it will be a continuous function type thing. In SPT, we get SPT. And other thing different than cone penetration test is that we get a sample here in this test. Because we are using this split spoon sampler, we actually get a sample at each SPT location. So that is about how and why we do the test. Let us talk about, actually, let me not do that. 1 second. Okay. So the other thing to talk about is that what kind of sample do we get from SPT. So you see, what are the types of samples? There are disturbed samples and there are undisturbed samples. And how do we know if a sample is disturbed or undisturbed? We calculate the area ratio of the sampler, and if it is less than 20%, then it is undisturbed, and if it is more than 20%, then it is disturbed. So typically, for a cross section of SPT, for split spoon sampler, let me write it here. We have an inner diameter of, it is almost 35, it is actually 34.93 mm, actually, because this is in LBS, it is basically 1 3 by 8 inch, and this is the DI, and the outer diameter DO, this is equivalent to 50.8 mm, about 2 inches. So let us calculate the area ratio for this. We know area ratio is equivalent to D outer square minus D inner square over D inner square into 100. Let us take in inches for now. So it is 2 square minus 1 3 by 8 square over 1 3 by 8 square into 100. Let us calculate this. So it comes out to be 111.6%. You will get the same results if you take in mm. So as you can see, which is much greater than 20%, which means it's a highly disturbed sample. Which means that it is only a representative sample. So there are some tests that you will be able to do on this sample and some tests that you will not. The tests that you need, in which you need to know the in situ conditions of soil. For example, let us write here the tests we can do and tests we can't do. Okay. So if we talk about the index properties, we can do that because it does not need the particular stress state condition from the soil. So we can do the particle size distribution curve for this. What we can't do is a direct shear test to know the stress versus strain. We can't do that. Roughly, we can calculate the uh, gamma B. We can take the water content of the soil inside. But any test that needs the initial condition, we can't do the consolidation test on, we can't know what is the stress strain condition here. So any test that needs a undisturbed sample, we can't do that. So we have to keep in mind that it is only a representative sample. It will not give us correct results for other kind of tests. Okay. The next thing that we want to talk about is, now that what we are trying to do is we are trying to standardize the test. We have already talked about the hammer weight, we have talked about the height of fall, we have talked about the depth of penetration. Now, there are some things that may be different in different tests. So, in order to standardize the test further, we have some corrections. Let's talk about these corrections first. Let's talk about the corrections of the equipment first, and then we can talk about the corrections of the soil. If there is a different type of soil, we will have a different type of correction. But let us talk about the correction of the equipment first. Firstly, there is a uh, one second. Okay. Firstly, there is a hammer correction. So basically, what hammer correction does is it is the efficiency. This is the actual hammer energy to sampler over theoretical input energy. Theoretical input energy is if exactly the whole weight of hammer without any losses was falling over this height on this sampler and all the energy was transferred. But we have this system of guide rods over which the hammer is moving. So there is some frictional energy loss here. Also, in the pulley system, you have two hoops here. Here also, you will see some energy loss. Due to falling of the hammer, there will be a frictional energy loss at the pulley and a frictional energy loss at the guide rods. So usually this is about um, 60 to in field it can vary from 30 to 90%, but the standard practice is to take 60%. And the SPT value corrected, like if we calculate the penetration for last 300 mm of the sampler, the number of blows if we calculate, and it gives us a uncorrected value n. And then when we correct it for hammer, we usually write it as n60, because usually we take the hammer efficiency as 60, but in our table it has been, in our question it has been given as 80. So instead of correcting with 60%, we will correct with 80%. Okay. The other factors of the equipment are borehole correction factor, drill rod length factor, and sampler correction factor. This is for the length of the drill rod that is attached to the sampler. This is for the diameter of the bore hole. So basically what we are doing is, in the strata, we are not inserting the sample by blowing throughout the strata. For example, here we have taken a sample and then we are augering or boring by any other means up to the next desired level for sampling, and then we are again installing the tripod for SPT, and then lowering the sampler, then attaching the hammer. And then after we have completed SPT here, we will take everything out. Then what we will do is, again we will auger or bore up to the next depth that we want, and then we will do SPT here. So basically we are augering or boring here, and then we are placing the sampler in this borehole. So the correction is for the diameter of this borehole. The next correction is for the drill rod length, as I said, that the sampler is attached to a drill rod, and for the length of the drill rod, there is this correction. And the sampler correction, as I said, that we use a standard split spoon sampler, but there are some variations. For example, if we are using this split spoon sampler with a, how do I put it, liner. It has a liner because, see, a split spoon sampler is the walls are quite thin, not as thin as they should be, like a Shelby tube, but they are thin, and the blows we get, these rods may buckle. So sometimes we use a liner here, um, and some for dense sands or something. And what kind of split spoon sampler we are taking, based on that we have these correction factors. Okay, and after we take care of these corrections, we have to correct for overburden and high latency. And this we will talk about while we are solving the numerical problem. Okay, so let's go back to the question and let's try to solve this. Let's draw a table for the depth and the n values, or let's convert this table into a column. Let's convert this. Uh, okay, I think that is a option given in Excel. So okay, let's take depth. These are the uncorrected blows. As you can see that the SPT sample is being taken at every 1.5 meters. So don't confuse the sometimes uh, students confuse the 300 mm to almost 300 centimeters, but uh, be careful about the units. So 1.150 mm is not 1.5 meters. Sometimes we get confused. Students get confused and do that mistake. That's why I'm mentioning 33, 29, 28, 29, 31, 35, and 41. Okay, so let us first correct for the hammer efficiency. We know the hammer efficiency is 80, so we will simply write this will be n into 0.8. So let's do that for this column. .5 into zero point 0.8. This is 20, 23.2, 26.4, 23.2, 22.4, 23.2, 24.8, 28, 32.8. So what you must know is that usually we do not take n in points. That is why you will see this in whole numbers, because number of blows as such cannot be in points. But right now, this is the first correction I'm making. If I convert it to a whole number at every step that I'm taking, so my error for the whole calculation will be magnified by manyfold. So let us take the points right now, and the final values that we get after making all the corrections, we will round that off to the nearest integer. Okay, so this was the first correction, hammer efficiency. The second correction is that the sampler is, let me actually write here. Okay, so our NH is 0.8, our NS is equivalent to 1, because you see it is a standard sampler. And what is our NB? Let us assume that NR for the drill rods is 1, and what will be our NB? Let's check our NB for borehole. So the diameter is 150 mm. So our NB is 1.05. So actually N corrected, or N80, let us write, is equivalent to N into 1 into 1.05 into 1 into zero point 0.8. As I said, that usually we take the value of SPT at 60 percent. So what we do is we multiply by NH and then we divide by zero point 0.6. So this will be our N60. Okay, our N60 is N into 1 into 1.05 into 1 into zero point 0.8 divided by zero point 0.6. So actually let us change this. Let us keep N60 here. That will be a better way of tabulating this. Let us calculate for each column. 25 into 1.05 into zero point 0.8 by zero point 0.6. Okay, calculate for all. Actually, our N60 will be a factor multiplied by N into 1.05 into 0 0.8 by 0 0.6, and 60 will be 1.4 times N uncorrected. And for the values in this column, we will have 35, 40.6, 46.2, 40.6, 39.2, 40.6, 43.4, 49, 57.4. So we will get these values for N60. That was the first stage. First thing is we calculate the N60, and these are the errors that we already talked about. Now, this is the second stage. These were the errors for the equipment. Now we will be talking about the errors that we have to calculate for the type of soil. Okay. So since in our question we have been given a coarse grained soil or a sandy soil, we should mention that there are two corrections that we do for sandy soils, that is, or coarse grained soils, that is correction for overburden and correction for dilatancy. Why we are doing correction for overburden is because if we are taking a if we are taking a sample from here, or if we are taking a sample from here, you see the confining stress in this sample will be higher because the overburden pressure is increasing as we go down, and there will be more resistance to penetration of the sampler here as compared to the same sample that was here. So as we go down, we make a correction for the overburden. For that, we calculate the overburden effective stress spread. And then there is either in IS code, there is a chart for correction of this, but that chart is also derived from the correlation given by Whitman, that there's a correlation given by Liao and Whitman that goes like Cn equals 1 by sigma naught dash by Pa. Now Pa here is the atmospheric pressure, which is equivalent to about 100 kilonewton per meter square, raised to power 0.5. So basically Cn is equivalent to Pa by sigma naught dash raised to power 1 by 2, where Pa is 100, and you will get a graph of this correlation of this form in the code also. Okay, so let us make this column for effective stress, and this column for Cn. So let me check. Okay, the gamma that has been given in this soil is bulk density is 18 kilonewton per meter cube, and saturated density is 19.5. Oh, kilonewton per meter cube. Okay, so based on this, so initially water table is very deep. So in the first case, in the first scenario, uh, we don't need to worry about the water table. So we just need to calculate the effective stress, which will be equivalent to depth times the bulk density. So it will be 18 into 1.5, 27, 54, 81, 108, 135, 162, 189, 216, and 243. Now, based on this, let us calculate the Cn value. This will be 1.92, 1.36, 1.11, 0.96, 0.86, 0.78, 0.73, 0.68, 0.64. So correction for overburden, corrected values. After correction for overburden, we will have N. Actually, it will be N160, which means at 1 atmosphere or atmospheric pressure, N160 will be Cn multiplied by N60. This is small. Okay, so let's calculate 27 into 1.92. No, 35 into 1.92 is 67.2. 40.6 into 1.36, 55.16, 46.2 into 1.11, 51.282, 40.6 into 0.96, 38.976, 39.2 into 0.86, 33.71, 2.78 into 40.6 is 31.668, 0.73 into 43.4, 31.682, 0.68 into 57 point, no, into 49, 33.32, and 0.64 into 57.4 is 36.736. Okay, so these are the values of N160 that we have obtained. So this is the C160. See, a bizarre thing about CN here we can see is that let me remove this. The bizarre thing about CN here that we can see is that based on its equation, Cn equals about 100 over sigma naught raised to power 0.5. See, when sigma naught is less than 100 kPa, our Cn will be greater than 1. And if sigma naught is, for example, equal to greater than 100 kPa, our Cn will be less than 1. So in this case, the value of n will be increasing because Cn is greater than 1. But in this case, after 100 kPa, the value of n will be decreasing because the value of Cn is less than 1. And this is what we can see here. Up till 81, we have Cn greater than 1, and Cn is after sigma is greater than 100 kPa, we can see that Cn is reducing based on this formula. Okay, so let us calculate now the yes. This is only for this formula. See, as I said that there is lots and lots of research. So we have many formulas the, besides this formula, and for those formulas maybe you will not get this condition, but this formula we discussed because this is the formula that is used by the IS code. Okay, so now let us actually now the second correction was the correction for dilatancy. You should know that this correction is only done for saturated soils, sands actually. Since our water table is quite below, so we will not be taking this correction in this part of the question. Our saturated sands, so why we take this correction in saturated sands is because when we apply impact loading on this hammer, there is a chance that there is liquefaction or development of pore water pressure here because this is saturated, and the and it is sandy. There is a development of pore water pressure. So what will happen is that as you blow, there will be a resistance which will give us a there will be a resistance due to the water here. It will take some of the loading when we are applying the load. So we do the dilatancy correction here in case of saturated sands only. So right now we will not be doing it because our water table, but for the last part we will be checking out the dilatancy correction also. So for now, let us calculate the final n value. As I said that we have to round off this n value to the nearest integer, and that will be the answer for our first part, corrected n value. Let me write n corrected. Okay, so this will be 63. This will be 55. This will be 51, 39, 34, 32, 32, 33, and 37. So now let us move on to the, okay, so these are the corrected values. Now let us move on to the next part. Estimate the soil friction angle. So as you must know that this is one of the most common tests that is being done in fields, SPT. And why it is the most common test is because we have correlations for SPT value and all the major properties of the sand. uh, for example, when we're talking about the coarse grain soils, we have a correlation for N and phi. We have a correlation for N and RD. We also have a correlation for N and E. So, but to calculate this, what we do is first we kind of estimate how many number of layers there are in the strata. Then we average out the N corrected for that layer, and then so we don't calculate the phi or the E for each of the SPT values, but for the strata. So for this strata, let us try to see how many values of how many strata there are, and then let us calculate the E and the phi values for those strata. If we talk about the relative density values for N corrected from 0 to 4, we will have a very loose sand. From 4 to 10, we will have medium sand, loose sand. From 10 to 30, we will have medium sand. 30 to 50, we will have dense sand. And for greater than 50, we will have a very dense sand. So let us try to identify it here for the relative density. This will be very dense, this will be very dense, this will be very dense. And throughout here, we will have dense. So let us suppose that this is one strata and this is another strata. So we will have an average N value here, average N value will be 63 plus 55 plus 1. about 56. And here our average n value will be about 34.5, or let us take 35. Okay, so for these values, our phi will be, let me give you the correlation for n and phi. Let me write it here. So this correlation is given by Peck et al. We have two correlations. One is given by Peck and the other is given by Schmertmann. Actually, there are three. Uh, Peck has given phi as a function of n160, while Schmertmann has given phi as a function of n60. Since we have already calculated n160, let's go on with the relation given by Peck. Phi equals 27.1 plus 0.3 n160 minus 0.00054 n160 square. So let's calculate based on this. This is phi dash. So actually Peck has given in a graphical form, and it was then given in a formula form by Wolf. So based on this, phi equals 42, and here phi equals 39, 37 degrees. Moving on further with the RD value, uh, actually let me write the equations for phi. And the same relationship given by Schmertmann is this 1974. You can refer to B.M. Das for this. This will give you in degrees directly. Here's y dash. Tan inverse n60 12.2 20.3 sigma naught dash over PA raised to power 0.34. There is another equation that is given by Hatanaka Uchida. (1996). They have actually given in terms of N178, but in terms of N60 it becomes phi dash equals under root 15.4 times N160 plus 20. So these are the three correlations with phi we can see. You can use any of those, it is not a problem. But you should know that the equations are approximate. Okay. Another thing is the relation between relative density. Let me write dr actually. The relative density and n. So Markuson and Vygotsky 1977 have given this relation where dr in percentage equals 12.2 plus 0.75 times 222 times n60 plus 2311 times OCR. No, there is a correction here. Plus 2311 minus 71 times OCR minus 779 sigma naught dash by PA. PA is 100 here. minus 50 times Cu square whole raised to power 0 0.5. Cu is the uniformity coefficient of sand. A is the atmospheric pressure. Other relation for Dr by Meyerhof in 1957 is given as N60 is equivalent to 17 plus 24 times sigma naught dash by Pa into dr square. So that implies dr equals N60 over 17 plus 24 sigma naught dash over Pa, and the whole is under root. So let us use this relation because we don't have these values. There are other relations like Kublinowski and Ishihara. Their relation includes a term for D50, or Kulave or Main. Their relation includes the grain size correct correlations. Let us for now stick to this for our question. And another correlation is between modulus of elasticity and N. So Kulave and Main in 1990 proposed this relation as Es by Pa is equivalent to alpha times N60, and alpha is equivalent to 5 for sands with fines, 10 for clean NC sands, and 15 for clean OC sands. Since we know that OC behavior, usually we are talking, when we are talking about OC behavior, we are talking about clays, and there is a analogy for loose sands with NC behavior of clays and dense sands and OC behavior of clays. So let us say dense sands here and take alpha is equivalent to 15. So our ES will be equivalent to 15 times PA is 100 atmospheric pressure N 60. So based on these correlations, let us now calculate the phi dr, the phi dr and ES. Phi we have calculated. Let's calculate the dr for this um, soil for these strata. Mm, Let me actually type it. So phi is 42 degrees. Dr, let us calculate from the Meyerhof equation, and Es, let's calculate from the Kullave equation. Here we have a phi of 37 degrees. And we need a Dr and an Es. Let's calculate the Dr first. For N is 56, but N60 is, what is N60? We also need, this is the N1 corrected average. N60 average will be, so for an average N60 value, let me do this. Yeah, this is N160, and let us calculate the N60 average for both the strata that we have identified. It's approximately 58, and let me copy this to here. The N60 average will be, sorry, it is 40.6, almost 41. Here it will be about 45. So the dr for 42 will be 42 over 17 plus 24 into, let's calculate the sigma naught at the center of the layer, which will be 18 into, so what will be the center of this layer? This is up to 0 to 1.5 to 4.5 minus 1.5 over 2. So it will be 1.5 root of 42 over 17 plus 24 into 18 into 1.5 over 100. So the dr will be 1.33. Let me check on BMDAS how this is calculated. There is one more relation that we can explore for dr. This is given by Skempton. Actually, let us do this relation only. Skempton in 1986 gave the relation n160 over dr square equals 60 for dr greater than 35. Let's calculate using this. Then dr will be excuse me 60 n160 over 60 under root. So let's try to do that. Under root of 56 over 60. Okay, so this comes out to be this comes out to be 96.6 relative density from Skempton's relation, because the dr is greater than 35. So if this was coming out to be less than 35, so this relation would not be used, and here it will be under root of 35 over 60. So this comes out to be 76.37 dr. So both of these are dense and very dense sands. Okay, and for ES we established this relation 15 into 100 into 160. And what will be the unit? Let me cross check. So the unit will be same as same unit as PA. Since we are taking 100 kPa, so our ES will also be in kPa. Let's calculate here. 1500 into N60. 41. So we get an ES value of 61500, and here we get an ES value of 67500. So this is the first four parts of these questions. Till now, what we have done is we have talked about the corrections in the SPT test. We have talked about the estimation of soil friction angle. We have talked about the relative density. We have talked about the estimation of average value of modulus of elasticity. Now, in the fifth part, it is asking that if the water table is at 30 meter, determine the corrected n values. So there are two things that will change now. First is that effective stress will change. So our first correction for overburden will change. And the second thing is that now we have to include the dilatancy correction. So let me copy this slide, take it to the end, delete all this. We also need to see N60 will be same. Now only the effective stress Cn, but only from here. Let me color this in a different color so that you will know that water table is below this level. Mm. Okay, below this water table is there. So these values now will be changing. So let's calculate the effective stress. Below the water table, we will be using not gamma saturated, we will be using gamma submerged. So our gamma saturated is 19.5. So our gamma submerged will be 19.5. Let us take gamma W is equal to 10. So our gamma submerged will be equal to 9.5 kilonewton per meter cube. Let's calculate the effective stress here now. 27 plus 54 plus 9.5 into 1.5. This will be 95.25. This will be 109 0.5. This will be 123.75, 138, 152.25, 166.5, 180.75. Okay, so let's calculate the values of Cn. So this is the effective stress now. Let's calculate the values of Cn. Cn will be same for the top two. Here it will be 95.100 divided by 95.25 under root 1.024. This will be 0.96. This will be 0.898. So it will be 0.9 actually. This will be 0.85. This will be 0.81. This will be 0.77. This will be 0.74. So N160, let's calculate, will be 33 in, no 46 into 1.024. This is 47.3. 29.96, 27.84, 28, 8, 25.2, 29.85 is 24.65, 31 into 0.81 is 25.11, 35 into 0.77, 26.95, 41 into 0.74, 30.34. Okay, now this will not be the end corrected value. Now we have to include the dilatancy correction, and dilatancy correction will only be included for the layers that are below the water table. So the dilatancy correction is applied after we have corrected for overburden. So N160 has to be calculated, and in N160 we get an N1-60 if N160 is greater than 15. If it is less than 15, then no dilatancy correction. If it is greater than 15, then N1-60 equals 15 plus 1 by 2 N160 minus 15. So since all our values are above 15 from here, we have to correct for all of them. If any of the values was below 15, we would not need to correct for that because it would come out to be negative. Uh, okay, so let us calculate for these 15 plus 7.5 plus N160 by 2. So N corrected after rounding off will be 31. One moment. Yes, here it will be oh, this will be 21.42. This will be, let's write 21 here because we are rounding off. This will be again 20. Again 20. So 21. Will be 23. Okay. So based on these corrected values, we get a different profile. What we get is this is what was the classification that we took for relative density? 10 to 30 medium. So this will be dense and this is all medium. So the rest of the procedure for calculating the N160, the phi, the DR and the ES is same. Only thing is that in this case we have to apply the dilatancy correction and we have to apply it only to those layers or only to those samples where the sample is underwater or under below the groundwater. And when we are talking about cohesive soils, these both of these corrections do not apply. So you have to keep that in mind. So class, that is it for SPT, our SPT question, and that is it for today. next week, let us talk about the next week of classes, the week 6. And if you have any questions, please ask me in the discussion forum. And I must still mention that why I have taken this question up was to kind of let you know that there are many empirical relations with between the soil parameters, as they are even very useful empirical relations, and they are being used throughout our this geotechnical engineering practice. Also, I wanted to let you know about the uncertainties in this test that can arise, because it is a very simple test, but when we simplify things so much, it they the their representativeness decreases. So we should be very careful while doing this test, which kind of parameters do we want to take and which kind of correlations. These are all empirical, and usually what we do is we try to see that the empirical relation given by a particular author, what was their case, what was their study, and if it is closer to our study, we use that relation, the one that is closer to our study. Some may be working on fine sand, some may be working on coarse aggregate or sands with mixture of boulders. And they specifically mention in their relations that this particular empirical relation is more valid, that will give better results for this kind of soil. So that is what we have to read into, that what is our problem and what are the relations given, and what a specific problem these are given for. Because you know that soil is a highly heterogeneous material. We assume it to be homogeneous, so that it cannot be a one shoe fits all kind of thing. We cannot do that with soil like we can in the metals, which have a crystalline structure, which is very um, perfectly perfect lattices. It has an isotropy to it, but soil is more um, a bit difficult to tackle. So we cannot one size we cannot give a one size fit all relation. So yeah, that is that was my um, motive for taking up this question. Thank you very much. If you have any question, please ask me in the discussion session, in the discussion forum.